Welcome back. We are now moving to lecture 27, and we are going to apply our knowledge from the previous lecture where we studied the real gas, in particular the van der Waals formulation for the gas, for the equation of state, to applications including cooling, and in particular we are going to look in Joule expansion. We are going to highlight the results, how they differ for real gas from the ideal gas that we have considered so far. So this course, this particular chapter will go a little bit beyond from what we have seen before, but it will be a great reminder of what the ideal gas law does and what the limitations are as well. The last part of this lecture, I will discuss the Joule-Kelvin throttling process, and we'll see how it's actually an application of all this business into the cooling of real gas in actual applications. So let's go back to a problem that we have been looking at from different angles since the beginning of this course, which is the Joule expansion. Remember the Joule expansion, we have two volumes like we have in the initial stage here, and there is the gas molecules from the left-hand side cannot move to the right-hand side initially. There is a vacuum in here, and then after a few seconds, you actually open this valve, and then you let molecule move here. Okay, this is the final state. Now, something that's very important, of course, it is an irreversible process. We've studied this at length, that the entropy has to increase. The experiment is set up so that there is an isolated system, so there is no heat in and out. And of course, during this process, when the gas move against vacuum, the PdV, P is of course 0, therefore there is no work done. So there is no heat exchange, there is no work done, therefore the total internal energy does not change. And we've seen this, and we know that the internal energy does not change, and we've looked at a number of consequences for the ideal gas. Now, we knew, of course, and I've insisted quite a bit on this, so that's the reason why it's a good reminder. For an ideal gas, the internal energy only depends on the temperature. So here, of course, since the internal energy does not change, that means the temperature does not change. So the Joule expansion of an ideal gas is not accompanied with any change of temperature. Is it the case for an actual gas, for a real gas? And so what we'll do in this lecture is to examine this for an ideal gas, and we will use the van der Waals description for a realistic gas moving beyond the ideal gas. So the question is that, is the gas going to warm up, cool, or remain at constant temperature? That's the question. To quantify this, we come up with the Joule coefficient, which is defined here in the red box. And the Joule coefficient gives you the change in temperature for a change in volume at constant internal energy. So the reason why we work at constant internal energy is because that constraint is actually imposed by the problem we are trying to solve. So sometimes students have a very hard time to understand where these constraints come from. Well, the reason why it's difficult to understand is that they are specific to the problem we want to solve. So remember here, this is kind of a given in the problem, that we are working in a thermally isolated system, and there is vacuum. So there is no change in internal energy, therefore we work at constant internal energy. And the change in temperature as a function of volume is what we are interested in this problem. So that's good. So we have this. It's just a summary of what we've done so far in the green box. This is what we start from. It's a good idea to do this when you try to solve a problem in thermodynamics, to know what you start from and what you have to solve. So we are going to move to the left from here, and we are going to remember this equation that we've used so many times. That's a mixture of the reciprocity and the reciprocal theorem that allows to write a partial derivative under a given constraint as a combination of a partial derivatives over constraints that are distributed. Don't forget the minus sign here. that will allow me to rewrite this equation here by promoting, if you will, the u inside inside the differential. Let's try to do this. Well, we see that replacing dt over dv at constant internal energy allows me to write it this way using the equation in the green box. And that's good because I'm going to know a number of things here. And first of all, we know, of course, how the change in internal energy as a function of temperature, well, it's exactly the heat capacity at constant volume, because we calculated constant volume. So of course it's the inverse here. So the change in internal energy is temperature is given here. Nice. So the other term here, we still don't know what it is. How does the internal energy change as a function of when you change the volume at constant temperature? It's going to depend on the model we use. So we are going to do that. We're going to go back to the first law of thermodynamics, where we can write du equal TdS minus P dV. And of course, that allows me to directly see what du over dV is at constant temperature. And what it is TdS over dV minus P. So directly getting this partial derivative from this equation. There's nothing really unusual here. It's always what we are trying to do is when we are stuck with a coefficient here, it usually means that we have to go back to the Maxwell's relations, and this is what we are going to do to look at ds over dv at constant temperature. And then we do this, ds over dv at constant temperature is dp over dt at constant volume, which is exactly what we do right here. So we can replace this differential. This is the typical approach that we have adopted since the beginning. Now this is nice, of course, because the equation of state, both the ideal gas law and van der Waals equation allow me to get to evaluate this term right here. Okay, so of course that means that this description will depend on the model we use, and I'm going to be able to replace this differential by this equation here, and I end up with this Joule coefficient that's giving me the change in temperature as a constant of volume. So you see, this is not a trivial function of temperature and pressure. So what's going to happen? So first of all, let's try to remember that for an ideal gas, the change in temperature with respect to when we change the volume at constant internal energy should be zero, right? Because there's no change in temperature when we keep the internal energy constant for an ideal gas. Remember, the internal energy of an ideal gas only depends on temperature. So that should be equal to zero. Well, we are going to see that right away. So let's try to understand a little bit this equation a little bit better. So first of all, we know that for the ideal gas, we should have mu j equals zero, right? Because for an ideal gas, the internal energy only depends on temperature. So if the internal energy is constant, the temperature has to be constant. And indeed, if you use the equation P equal RT over V, you will see that the difference between these two terms is going to be equal to zero. This is pretty easy to see. So indeed, mu j is equal to zero simply because in ideal gas, the internal energy only depends on temperature. Now, is that the case for a realistic gas? It turns out for a more realistic gas, we do actually get cooling. And I'm going to show you in a minute that this is due to the attractive interaction. I'm going to discuss that in the next couple of minutes. But before we do that, before we have a discussion about what's happening during the actual experiment, let's try to remember what we found on the previous slide as a intermediate result. We found that mu j was equal to -1 over CV d over dv at constant temperature. So one thing that's very, we obtained this from the reciprocity and reciprocal theorem from if you remember the equation in the green box. One thing that's very confusing to students is that they remember that what they are trying to model. They're trying to remodel this Joule expansion, which of course happens at constant internal energy. Now, it turns out that the math and all the fact that we are working in a formalism that's accurate, of course, because of the math, we end up with this term that actually depends on partial derivatives that do not necessarily directly correspond to the experiment. Let me try to explain here. the change in internal energy as a function of volume at constant temperature is not, these are not the actual conditions under which the Joule expansion takes place. However, it turns out that this product here, all the combination of all those calculations, the evaluations of those partial derivatives, leads to the same result as we would have with the actual experimental conditions. So I hope this is clear. My point is that this makes perfect sense to calculate this derivative here because of the way we built it mathematically from partial derivatives. So why is the mu j negative? So why do we have cooling? So remember, mu j is a change in temperature as a function of volume at constant internal energy. Well, 1 over CV is certainly a positive number. And so it turns out that du over dv at constant temperature is a positive number as well. And so because of the negative sign, we get a negative change. So why is that a positive number? Well, imagine the molecules that we have described, for example, in the van der Waals description of the realistic gas. But you can use the other models as well, if you will. Usually at the distances at which the molecules are located, you are in the attractive part of the potential. And when you're at the attractive part of the potential, we know that the attraction is less and less negative as you increase the distance between the molecules. So if you increase the volume, okay, if you increase the volume on average, the distance between the molecules is going to go down. I'm sorry, it's going to go up. So if it's going to go up, that means that the internal energy is going to go up. In other words, the system is less stable, so you have less attraction. Okay. So if du over dv, if that's it, is going to go up, so it's a positive number, and therefore we see mu j is equal to is smaller than 0. And we can also calculate the change in temperature, of course, by simply integration. So let's go back a little bit now. Instead of using the math that we have here, let's go back to the actual experiment that we do in Joule heating. And so the idea is the same as I said before. When you change the volume, you know, because you have no choice. The constraint is that the internal energy has to stay the same, right? It has to stay the same just because there is no heat that comes in and out and there is no work performed. Now, when you increase the volume, you know that the attractive part of the potential, and this is this piece here, when you increase the volume, the attractive part is less negative. So basically, it's like you started from here and you end up this way because you increase the volume. You increase the average distance between the molecule. Now, when you do that, you increase the energy. Okay, you increase the energy, but the total energy has to be constant. That means that what has to go down is the velocity of the molecules. But the velocity of the molecules are related, the sum of the square of the velocity, actually the sum of the velocity is related to the kinetic energy. So that means that the molecule basically have to go slower, if you will, and that means the temperature goes down. So this is indeed the square of the velocity. Of course, is the kinetic energy mv squared over 2. So this is reduced, and therefore the temperature falls. So that's the interpretation that we have, why we have cooling in the Joule heat, in the Joule expansion, not the Joule heating, in the Joule expansion. Let's try to see this mathematically now. So this is what we found on a couple of slides ago, and we know the description of P, and this is a description we had from the previous lecture. Calculate the derivative, and if we substitute these two terms inside on the left-hand side, we end up with mu j, which is equal to minus a cv over v squared. Now a, remember, that was the positive term that we used for the attraction between the molecule. Cv, of course, is the heat capacity at constant volume, is a positive number, and v square is the volume square, so positive. So of course mu j is indeed negative. So in other words, you have cooling. Now, one thing that you can wonder, and of course you can also calculate temperature change from this just by integration. I'm sorry. So one thing that you may wonder is that why does it only depend on A? Remember that the model that I described to you, the van der Waals model, depending on both A and B. Well, it turns out, as I said, during the Joule expansion, the part of the potential that we are really observing and exploring is the attractive part, which is the A part. We do not increase, for example, if we were increasing the pressure and bring things very close together, of course we would start to feel the repulsion between the molecule, but not in this experiment. So this is the reason why it only depends on A. Now we can also now get some bonus from everything we've done, because it turns out, because of the math, we had to calculate du over dv at constant temperature. Remember from the reciprocal theorem. But this particular partial derivatives, correspond to the isothermal expansion. Of course, isothermal expansion means that you are changing the volume at constant temperature, right? You expand, so that's change of volume, isotherm at constant temperature. So in that case, we know, and we've seen this before, that this term is not necessarily equal to 0 in the general case. And we've actually calculated it again a couple of slides ago using Maxwell relations, and we obtain this term. Of course, we've seen that this term is going to yield this particular term if we want to calculate the net change in internal energy. The ideal gas, of course, is no change. This is going to be 0. Again, no surprise. If we do an isothermal expansion, so if we keep the temperature constant, of course, the internal energy has to stay the same, since the internal energy only depends on the temperature. Now, this is not so for the van der Waals gas, and then you can calculate that when you expand your system isothermally, you will see that you have you can see a net change in internal energy, and of course, usually V2 is larger than V1. Therefore, this term is positive. So you have an increase in internal energy, and of course, we understand the increase in internal energy. Remember what we said before. The internal energy, there were two parts. There were the part coming from the interaction between the molecules, and there was the kinetic energy. But in this case, the kinetic energy does not change since the temperature remains the same. But we also have an increase in we have less attraction. Therefore, we have a net positive change in the potential. Therefore, delta U has to be positive. So what I like to remind you, we looked at two problems here. The first problem is the Joule expansion is in the Joule expansion we are not isothermal. We are adiabatic, and we work against there is no work, so there is constant internal energy. And the isothermal expansion is also an expansion, but in this case it's at constant temperature. Okay, so it's clear. So that's nice. We have all this. And we can calculate the entropy of the van der Waals gas now. We can reuse this definition of the exact differential of the entropy. Remember, the entropy is an exact differential. And so we can calculate this way, as using the partial derivatives. And one more time, we can make the changes using what we've done in chapter 16 when we look at chapter on the entropy, when we actually again mostly used the Maxwell relationship. And so we can now calculate, of course, a change. We can now calculate this entropy using the equation here, the specific equation for the van der Waals gas. Okay. And so what we find in that case is that the entropy is going to be equal to CV ln T. So this is when I integrate. When I integrate, I get a logarithm of temperature here. And when I integrate here, I get, of course, an integration of this term. And I also get a logarithm with respect to volume. Okay, and then, of course, I have a constant. When I integrate, I always have, I need to have a constant of integration which I don't know. So I find that the entropy is behaving like this. And of course, when B is equal to 0, I obtain the result that I had for I get the result that I obtained for the ideal gas, of course, for B equals 0. But it turns out that as B changes, we see that the entropy goes down. So when B increases, the entropy goes down. So this is interesting. So that means that there is basically less disorder as B increases. This is not very surprising because B is the excluded volume, right? It's the volume basically that is not open for for access for the other molecules, right? This is the repulsion. So basically, when B increases, you decrease the number of states that the other molecule can assume. Therefore, the number of microstates goes down as B increases, and therefore that makes sense that the entropy would go down as B increases. So this is what's interesting. And of course, A has nothing to do with the number of microstates. B does. B basically removes space available to the molecules, but A does not do that. So the entropy only depends on B. So that's very interesting, as opposed to the internal energy, the change in internal energy that only depends on A. Now you may wonder that it's all nice and good. We can calculate, we can actually cool a gas, and that's good, but that's not really a practical solution to cool down a gas. The reason why it's not a practical solution is because we have to separate the gas on the left and the right between the vacuum and where the molecules are contained initially. So that we would prefer to have something more continuous. And this is what the Joule-Kelvin expansion experiment does. So this one is a little bit more complicated, and I'm going to explain that to you in the rest of this screencast today. So the schematics for this expansion is explained here. So basically we have two containers on the left and the right, and they're connected here by a channel, or by a tube, basically between the two. There is a high pressure on the left-hand side. It's going to be P1. It's going to be considered a high pressure. And there is a low pressure on the right. It's going to be written P2. And so the idea here is going to be moving gas from the left-hand side through this constriction, so through the porous plug, to the right-hand side. And so the idea, and we are going to show this now, is that by doing this, we are going to decrease the temperature. I mean, we can decrease the temperature of this gas from the left to the right. So we are going to analyze this. Of course, this particulate setup is different from what we had before. We are no longer in a situation where we have the internal energy that's conserved as we had before. First of all, there is work done. Okay, we may have this thermally isolated, but there is work that's done on the left and on the right. So clearly, the internal energy is not constant. It turns out there is another function of state that's conserved instead of the internal energy, and this is what we are going to do now. So what's the change in internal energy? Well, the work done to move V1 against P1, which is exactly what we have to do here, is of course P1 V1, right? We've seen this before. P1 V1 is the work done to move V1, but we also have to move the volume V2 against P2, right? So this is a work P2 V2 on the right hand side. So in other words, if we want to look at the change in internal energy, the change in internal energy is going to be related to the difference between the work on the left and the work on the right. In other words, mathematically it means that the internal energy 1 plus P1 V1, so on the left hand side, is going to be equal to U2 plus P2 V2. If you do remember, which I'm sure you do remember the chapter on thermodynamic potential, U plus PV was defined as the enthalpy. So what we see is the enthalpy before and enthalpy after, so H1 and H2 have been conserved. So in other words, we are working at constant enthalpy. So that's nice. It's basically it's nice because it basically means that we can repeat all the machinery we did for the Joule heating, but now for the Joule-Kelvin for the Joule expansion, but now for the Joule-Kelvin expansion, but now under a different constraint. Instead of having the constraint of constant internal energy, now it turns out that the constraint we have is the constant enthalpy. And I'd like to insist this constraint does not come out of the sky. It comes from the fact that this is how the device was built. The device was built such that the work done on the left and is a change in internal energy on the left, and the work done on the right is a change in internal energy on the right. And this is what's conserved here. That's what's important. So, of course, we come up with another coefficient. Instead of using the Joule coefficient, which was dt over dV, because we were changing the volume at constant internal energy now, the Joule-Kelvin expansion coefficient is going to be the change in temperature with respect to pressure. So it's how we move a gas from pressure P1 to P2. And now we know that the constraint is conserved enthalpy. This is what we are going to calculate. So this is this term that we are interested in, and funny enough, we are going to follow exactly the same procedure as we've used for the Joule expansion, but in this case we are going to use different equations because we are working at constant enthalpy. So using the reciprocal, because we are working at constant enthalpy. Now, using the reciprocal theorem and the reciprocity relation, we can rewrite again this derivative the same way as we did before for the Joule expansion, and we find that one more time we can calculate all these things. And then in particular, we will remember the definition of the heat capacity at constant pressure, which is a change in enthalpy as with respect to temperature, calculated at constant pressure. And then all we have left to calculate is the change in enthalpy with respect as a function of pressure at constant temperature. And we are going to use the same tool as we did before, is to find how to calculate this. And of course, for this, we are going to write the differential, the exact differential for the enthalpy. We remember TdS plus VdP. And that allows me to write that the partial derivative dH over dP is, of course, V plus the change here that I have at constant temperature. So this is what I end up with. Very similar to the case of the Joule expansion, but here, instead of using the relationship with the internal energy, I use a relationship with the enthalpy. So using Maxwell relation one more time, that allows me to replace this derivative, which is not an easy derivative to calculate. It's a change of entropy with respect to pressure. It turns out that this is nothing else than minus the changing on volume with respect to temperature, which is clearly an easier thing to do, to calculate or to measure. So this is all good and nice. Now I can substitute this term from my intermediate, my temporary relationship for the Joule-Kelvin expansion coefficient, and I end up with this term, which is very similar to what I had before for the Joule expansion, but now it's under different constraint. So one more time, you can calculate, of course, a change in temperature when you move from pressure P1 to pressure P2, and this is calculatable using the different models that we have. Now I'd like to spend a second here to compare this with the Joule expansion. So remember the constraints are different. In the Joule expansion, we are changing the volume, and in the Joule-Kelvin expansion, we are changing the pressure. Right, that's what we are doing. Now we remember that the natural variable for the enthalpy is the pressure here. So this is the reason why we are working at constant pressure. And another one of the natural variable for the internal energy U is the volume. Remember, minus PdV. So V is a natural variable. So that's the reason why we work at volume at a constant volume. Now it turns out that the other terms that we have here, minus V and minus P, come directly from the term related to the correction we make, the difference between the internal energy and the enthalpy. So this is how you can draw the parallel between these two equations that will correspond to two different experiments and two different constraints. Good. So let's try to study a little bit here. We saw that for the Joule expansion, we're cooling the gas, right? If we increase the volume, we cool the gas. But is that going to be the case for the Joule-Kelvin expansion? Well, it turns out that is much more rich than what we find for the Joule expansion. It turns out that we have something a little bit more complicated for the Joule-Kelvin, and this is what I'm going to do in the next slide. Actually, the slide after this. If before that, I'm going to look at the change in entropy. Now, change in entropy turns out to be easy to calculate because since the enthalpy, the change in enthalpy is TdS plus VdP, but we know that the enthalpy is constant, is a constraint of the problem, we can directly calculate the change in entropy as minus VdP over T. So that means that we can integrate between the two pressure and obtain this relationship right here. Very good. So for an ideal gas, we can calculate this easily for an ideal gas. So if we go from one pressure to the other one, we had positive entropy, and of course it makes sense since we have an irreversible process, we'd see the change in entropy. We can calculate this as well for the other models, but you get a result that's similar, that's positive. Now, here's the big question that we ask. Is this term positive or negative? Well, let me, again, spoiler alert, it can be either. It turns out that depending on how the volume changes with temperature at constant pressure, we are going to have, this is going to be either positive or negative. So let's try to see this, how it works. So this is going to change sign, so it's going to be either positive for an increase in temperature, so warming, or negative for a decrease in temperature, for cooling. And this is going to, the crossover between cooling and warming is going to happen when this term here is equal to V over T. So in other words, when the change is zero. So it's zero because it goes from positive to negative continuously. So the points, the values in reality in the system where this is going to be true is going to be an inversion curve. An inversion curve is usually a curve if you go on one side of the curve, you get a behavior, and if you go on the other side of the curve, you get the opposite behavior. So let's try to see here that those two behaviors are either warming and cooling. So the best way for this is to plot this. So we are going to spend quite a bit of time to explain this figure. So do not panic. So here we are essentially plotting the temperature with respect to pressure for a van der Waals gas, and of course here we are using the reduced coordinates by dividing by the critical temperature. We do that simply because we want to have universal features, as we discussed in the previous lecture. So. And each of those lines correspond to a constant enthalpy, so isenthalps. Okay. So let's try to explain all the features we see here. So first of all, let's try to remember the definition of the Joule-Kelvin expansion coefficient. This is the change in temperature when we change the pressure. Remember, we had the pressure on the left, pressure on the right, and this is exactly what we are doing. We're trying to understand how is the temperature changing when we impose a gas to go through a high pressure, from a high pressure to a low pressure at constant enthalpy. So this is what we're interested in. Now, it's nice because all those curves are indeed temperature with respect to pressure. Okay, so it turns out that this term is, when we look at those graphs, we see that it can be positive, which would be warming, right, increase in temperature, or negative. Okay, so it turns out that one thing that's again very confusing to students sometimes is that, remember that here my pressure is going down, right? We start from a gas at high pressure and we move it to low pressure. So what we're really interested in is how the pressure here, the change in pressure is a negative number. So we go to the left-hand side. So what happens when we go to the left? Well, it turns out that the delta T over P is going to be, so this is going down. So in other words, the dt over dP when dP is negative, is going to increase. So we have a warming. So basically, we start from a temperature, and we go up in in temperature as we go to the left. Remember, we have a decrease in pressure in the experiment. Now, the same way, we also, when we have the positive slopes correspond to a negative mu. I just like to be clear, because you say this is very confusing to students. Well, if it's a positive slope, this number should be positive. It's not. It's actually positive slope, yes, but the pressure is actually negative. Okay, so that means basically the gas is actually cooling as we go down in pressure to the left. Okay, so you go down in pressure to the left, the temperature goes down. Okay. So in other words, if I go to the right, if the pressure goes up, the temperature goes up. So this is what it's doing. Okay, good, very good. So this is what we obtain in this equation. And of course, in between those two regions, we have the inversion curve, where if we work at those pressure and temperature, we see that actually during this experiment, we have an inversion curve when the temperature does not change. So this is important. This is nice. So that means that in the Joule-Kelvin expansion, you can have either warming or cooling of the gas, depending at which temperature pressure you are starting with. There are more features to look at in this graph, so let's try to look at them each one by one. First of all, remember my critical point. The critical point is, of course, much lower. Remember, critical point is where you start to have the coexistence of a gas and a liquid. This is actually when you start to liquefy your gas. So, of course, it's a much lower temperature when you start to liquefy. In fact, it's 1,1. Why? Because it's a critical point. And by definition, since I normalized the temperature and the pressure by the value at the critical point, of course, this point is a 1,1 point. I also have this little curve here, which is actually the coexistence of liquid and gas. This is what we studied as well in the last lecture. This is when we go across this line, we have a sharp change from liquid to gas, or from gas to liquid. Nice. Now we have something more. We also have the maximum inversion temperature. And the maximum inversion temperature is right here. I hope you see my pointer. This is an important point, because imagine that you are at higher temperature. Let's imagine that you are at this temperature. At this temperature, you can change the pressure any way you want. You will never cool down. You will never be in the cooling down phase. You will always warm up. So the point is that you always have to work at least at this point or lower in order to cool down your gas during the Joule-Kelvin expansion. And these are here some values that you can find in the literature for different gases where this maximum temperature takes place. If you start to work at a higher temperature to cool it down, you can't. So if you try to cool down, for example, helium from room temperature, you have to find different methods to do it, because it can only start to cool down at 43 Kelvin using this Joule-Kelvin expansion. For carbon dioxide, it's different, and so on and so forth, of course. And this is all due to the interaction between the molecules. So that's nice. Now it turns out that we can even go as far from the previous graph to the liquefaction of gas. And so the Joule-Kelvin process, of course, we have to start below the maximum inversion temperature so that we do actually cool down. And so we can cool down the gas, and then we can use the cool down gas to pre-cool down the gas we start from at a high pressure. So I'm not going to insist too much on this. The point remains that you can actually liquefy and go all the way down to the critical point on the graph I showed on the previous slide, and end up with liquids, with the liquid start. And the idea is to expand the gas from a high pressure to a low pressure. So this is how you do the liquefaction of gases. So this is something that's studied quite a bit, and I'm here just not insisting too much. I just like to provide you an overview of what we call the efficiency of this liquefier. More information provided in the textbook that we have been following in this course. And so remember how it works here. We have high pressure compressed gas. It goes into this very fine, this small tubes towards low pressure, so the final pressure. And so the idea is that we hope we use this system to actually get some liquid out of this. Okay, so so of course everything that we have on the left and that we have to start is to be found at the end. So we have 1 kilogram of gas. We need to have 1 minus y kilogram of gas and y kilogram of liquids. In other words, the sum is the same on both sides. So enthalpy is initial enthalpy, the final enthalpy, and the liquid enthalpy. Same for the temperatures and same for the pressure. We can define all those things. What's nice, of course, we know is that this system is worked at constant enthalpy. So we can also calculate the enthalpy here. The enthalpy, we can of course calculate the enthalpy of the initial gas as a function of the enthalpy of the end. So basically we have the enthalpy of this plus the enthalpy of this with the weighted from how much of each we have. And this is due to the fact that the enthalpy is conserved in this process, in the Joule-Kelvin expansion. And so we can calculate the efficiency, which is, of course, y. The y is the amount of liquid. So we want this to be maximal. We want to have as much liquid as possible in this process. And then you can calculate y from this equation, and you find that the y is the difference in enthalpy between these two processes, one gas to the other, and these two processes. And of course, you want this to be as close to 1 as possible. So it turns out that so everything I provide here in the text is what I just said. So what if we want to optimize the efficiency? We want to find what is the enthalpy, for example, the initial enthalpy that we have to use in order to maximize the efficiency. And of course, we have here an optimization problem where we have to simply calculate the derivative of the derivative with respect to pressure that we have to calculate. And so when we do this, when we calculate this, and I do not insist too much on this as it's explained in the book, and it's not fundamentally different from what we've done before. When we calculate this, we find that this particular optimization constraint leads to the fact that the Joule-Kelvin coefficient should be equal to 0. This is where this point here, so when the inversion curve, remember the inversion curve is when the mu was changing sign, so the inversion curve is the place where the efficiency of this liquefier is optimal. Okay, so this is how we want this would be how we would like to use such a device to get an inversion curve. So what I like you to realize in this lecture is of course this is an important slide here, but the most important slide was the previous one where we were able to analyze the different regime, heating versus cooling, and also put it back into the context of the liquefaction of gas, which of course happens at much lower temperature. So this is a summary of this lecture. We've spoken about Joule expansion in a real gas. We calculated the entropy, and we also calculated the change in temperature. And then we also introduce another experiment, which is the Joule-Kelvin expansion, which can be actually performed at a steady flow. And the reason why we can do this is because the volume is not fixed, if you will, but we actually what we fix is a change in pressure. So we have a high pressure going to a low pressure, and we realize by a simple analysis that the Joule-Kelvin expansion actually takes place at constant enthalpy instead of constant internal energy as you would have for the Joule expansion itself. And then we calculated how we can understand that this process can either cool down or warm the gas depending on where you are in phase space, so in the pressure versus temperature curves.